In this lesson, we're going to take a look at weak acids. So we looked at strong acids and acids and bases in general in our last couple of lessons. So some examples of weak acids are citric acid, acetylsalicylic acid, formic acid, and carbonic acid. So one of the things that we talked about was strong acids have a pretty much 100% ionization when they are in water. So it's over 99%, which we just assume as 100%. Weak acids, on the other hand, have less than 50% ionization. So it depends on the acid where that falls between 0 and 50%. So the percent ionization we can calculate by taking the hydronium ion concentration divided by the concentration of the acid that we started with, and then multiplying that by 100. So general formula for a weak acid is our acid dissociating in water to create hydronium ion, and then the acid without the H there. So once again, we have the acid ionized is hydronium, so the concentration of that over the beginning concentration of the acid that we had. And remember, this is really H3O+. Okay, so an example of a calculation that we would do. The pH of a 0.1 molar methanoic acid solution is 2.38. Calculate percent ionization of methanoic acid. So methanoic acid, if we take a look at the formula for dissociation, so when it's in water, some of it will become that and some will become hydronium ion. So we know the starting concentration of methanoic acid, and we know the pH of the solution. So if you remember from our last lesson, we learned that from pH we can calculate the hydronium ion concentration. So 10 to the negative pH. That's hydronium ion concentration. So 4.17 times 10 to the negative 3 moles per liter is our concentration of the hydronium ion, and then the percent ionization is equal to the hydronium ion concentration divided by our starting concentration of our acid. So we're looking at how much of what we had ended up becoming hydronium. So 4.17 times 10 to the negative 3 divided by 0.10, and times by 100 to convert to percent, which gives us 4.17%. So 4.17% of our methanoic acid will dissociate. Okay, so our ionization constant for acids is Ka, and similar to Keq, except that we don't use water. So our general formula, once again, Ha plus water becoming hydronium ion and A minus. So that is our acid and then conjugate base. So Ka is equal to the concentration of the products over concentration of reactants, and we don't use anything in the pure state, so water as a liquid we don't include. So that's the difference between Keq and Ka. The same would be true for Kb, which is the ionization constant for bases, although we're not going to be looking at that this semester. So we'd have OH instead of H3O+. So if you see that next year in chem, then it's just the same as Ka. Okay, so once again, we're not including water or anything with a pure state. So the stronger the acid is, the larger the Ka is. So the stronger an acid is, the higher the percent of dissociation is, which means the higher our concentration for our products is going to be. And we can find known Ka values, so these are at 25 degrees Celsius, and you can find those on page 597 and 747 of your textbook. Okay, so second example, a 0.24 molar solution of carbonic acid has a pH of 3.49. Determine the Ka for H2CO3 when 1 hydrogen is donated. So, carbonic acid and water, and dissociating with just 1 hydrogen. So I know that I have 0.24 molar to start with. At the very beginning I don't have any of those. And then I have a 1-to-1 ratio here. And this is also 1-to-1 ratio. So I can determine my hydronium ion concentration from my pH. So hydronium ion concentration is 10 to the negative pH, which is equal to 3.24 times 10 to the negative 4. So that means that those x's then are going to be 3.24 times 10 to the negative 4. And my final concentration there then is equal to 0.24 minus 3.24 to the exponent negative 4, which is 0.239676. So Ka, so we'd have the same type of expression, products over reactants, except that we are not using water, which is in a pure state. So concentration of HCO3 minus and H3O plus, and all our exponents are 1 because all our coefficients are 1, and H2CO3. So I have 3.24 times 10 to the negative 4 times 3.24 times 10 to the negative 4 for my products, all over 0.239676, which is equal to 4.38 times 10 to the negative 7. So my Ka, or ionization constant, for this acid is 4.38 times 10 to the negative 7. Okay, next example, calculate the pH of a 0.1 mole per liter ethanoic acid solution if Ka is equal to 1.74 times 10 to the negative 5. So ethanoic acid, CH3COOH plus water. Okay, so to start with, I have 0.10 and 1-to-1 ratio, and no water, so starting with 0. Okay, and Ka is equal to CH3COO minus times H3O plus all over concentration of CH3COOH. And I know that my Ka is equal to 1.74 times 10 to the negative 5. And then I have x times x, or x squared, all over 0.10 minus x. So to find the pH, I'm going to need the hydronium ion concentration, which is my x, so I can use my Ka expression here to solve for x. So I'm going to take my 0.10 minus x and multiply it over by the 1.74 times 10 to the negative 5. So that gives me 1.74 times 10 to the negative 6 minus 1.74 times 10 to the negative 5x, and that equals x squared. And if I move everything over to the other side, so now I can plug this into my calculator to solve for x, and that gives me either x equals 1.31 times 10 to the negative 3 moles per liter, or it equals negative 1.33 times 10 to the negative 3. And that doesn't make sense because I can't have a negative concentration, which means that my hydronium ion concentration is equal to 1.31 times 10 to the negative 3, and I can now use that to solve for pH. So pH is equal to negative log of my hydronium ion concentration, which is equal to 2.88. Okay, and the last example I'm going to do, so calculate acid ionization constant, so Ka of acetic acid, if a 0.100 molar solution at equilibrium has a percent ionization of 1.3. So we have, again, acetic acid, so CH3COOH plus water dissociates into acetate ion and hydronium ion. So I know that I have 0.100 to start with, a 1:1:1 ratio. 0.100 minus x, and x there. So Ka is equal to my product, so acetate ion concentration times hydronium ion concentration all over acetic acid concentration. And I don't know yet what those values are, but what I do know is percent ionization equals my hydronium ion concentration over my ethanoic acid concentration times 100. And the percent was 1.3. I don't know hydronium ion concentration, but I do know that my initial concentration for acetic acid was 0.100. So if I take 1.3 and multiply it by 0.1, divide by 100, x equals 1.3 times 10 to the negative 3. So that means that my hydronium ion concentration and my acetate ion concentration are both 1.3 times 10 to the negative 3. And my acetic acid concentration at equilibrium is 0.1 minus 1.3 times 10 to the negative 3, which is 0.0987. And when I solve for that, it's equal to 1.71 times 10 to the negative 5. So the acid ionization constant, or Ka, of acetic acid in this situation is equal to 1.71 times 10 to the negative 5. Some practice questions to work on are on page 400, numbers 19 to 24, and this once again is old textbook, so you can find the files either on the hub or at the end of this slideshow.